Hello, Justin.
Hello.
So what things?
I'm doing pretty good. Pretty good. Got the weights set up last week, so I'm a bit sore from getting back to the weights yesterday.
Good.
Yeah, how are you doing?
Yeah, doing fine.
Good.
Yeah, doing fine. No complaints with the classes yet. I think it seems to be going good to me. Yeah.
Yeah.
It doesn't seem to be hampering too much of the flow, I guess.
All right. Yeah, that's good. All right. You and your wife staying safe? No, no illness or anything?
Yeah, I don't see anything. Yeah, we are doing good.
Good.
Yeah. And even my family back in India, they're all good. Yeah.
Good.
What about you? Your friends? Anyone? You never talked about your friends or anything?
Right. Yeah. So far, I haven't. Nobody that I know of has come down with anything.
Yeah. Let's keep it that way. Not that we have any control.
Right. You know, it was interesting. I was looking at some of the different stats around the globe for the virus, and I noticed that in India the numbers of cases and deaths were significantly lower than they are not only in the U.S. but in many other countries in Europe and places like that have significantly smaller populations in India. So
that's right. Don't ask me why.
Right.
Yeah, it is very low, and even the spread has been significantly lower. One could argue that it could be because of the less number of testing.
Okay. Yeah. Okay.
But at least I know in one state, and they are doing sufficient tests, and still the numbers are low.
Right.
Yeah, don't ask me why. Yeah. Maybe Angela has one. Hey, Angela.
Hi.
Just curious, or not curious, I would say he was pointing out that the number of cases in India are significantly lower.
Oh, because we don't have testing kits. Like some of the rough statistics is 5,000 for a million people, and then India there are like 9-10 testing kits for a million people. I mean the number of, I mean probably not a million, probably like a couple of 100,000s, but we don't have enough testing kits. That's why there are like much less number.
That's it.
But it's like, yeah, that's the whole point. Pretty sure the case is as bad as in India also.
See, I thought maybe they're just doing something way better over there than we're doing here.
Sorry?
I just thought maybe they were handling it way better than we are or something.
I've heard Kerala is, but I don't know about the rest of the country.
Yeah, I also hear that Kerala, it seems that, would it be correct to say that they are doing tests also in Kerala? There are sufficient.
They're doing?
That's what I thought, but I don't want to claim anything. I'm not well.
They're doing what?
the testing is reasonably being done in Kerala.
That's what I've heard. Generally, they're trying to combat the situation much better in every way. I mean, maybe we could be biased, like maybe the news I am reading would be biased, but I mean, they have experience with all the Nipah cases and all, they handle it pretty nicely. So I guess they are much more experienced with all sorts of disaster management, like floods and everything. They're used to it. So I guess, I'm guessing if they're much more experienced than the rest of the country.
But then it could be late also, so we cannot say anything.
Yeah.
So now it's just beginning. So the point is, until the curve goes down, we cannot say anything. Yeah, I don't know. But there are other countries also, right? From like Singapore is another example where
South Korea and Singapore handled it pretty nicely, I think. They recovered from it pretty good. I have heard that people, the Singaporean government asked the SIU students to come back to Singapore because it's much better there. The cases are much better. Yeah, SIU government, like a friend of mine said that all of his Singaporean friends, they left last week or something. Yeah.
I know Yusa, or Yasu rather, he went back to Japan, I think it was last week or something. I don't know if that's why, because of a better virus, what management, I guess.
But I would assume traveling at this point is actually quite risky.
Yeah.
Right? I mean, going from airport to airport, where most of the people are actually right now doing that, I would assume that, but maybe the government has a different idea in mind. A particular aircraft for all the people going to Singapore, something like that. I don't know.
Yeah, I too would think the same. So Yasu has gone back. Is that what it is? I don't know.
Yeah. He emailed me last week actually. He was looking to sell off his furniture because he was leaving.
Yeah.
Got it. Okay. Yeah, the travel is a risk, I would think, but then.
My father actually asked me to come back home like 2 weeks ago. He's like, I'm like, I probably don't think that's a bad idea. It's okay if I drop the semester and come back, it's fine.
Yeah. Because parents always think that they can take care of kids better than alone, so that's understandable. Yeah. But that comes with the risk of travel, I guess.
Yeah. It's already 18 hours of travel, which is like a huge hurdle. And then on top of that, with all the immigration procedures being much more strict right now, it'll be like a day or two by the time you reach back home.
And you will have to go through quarantine too, right? If you go back, they're not going to treat you very well. And in India, Indian societies, they don't respect this quarantine so much. They almost consider it as.
My father traveled from Abu Dhabi like 2 weeks ago, and he was in self-isolation for 2 weeks. Like he was distancing from my mother. He was in the upper floor, and my mom was in the ground floor. Like they were living separately in the house. They extended the quarantine to like 4 weeks now. I don't know how that's valid, but it was supposed to be 2 weeks, and now it's 4 weeks.
That's a nationwide quarantine.
There is a nationwide self-isolation sort of thing, like you're not supposed to leave the house. I mean, we have stay-at-home orders, but it's not that strict, right? But there, like the police that's there in different places, they literally beat you up if you come out of the house.
Oh, wow.
There are so many videos of police beating up people.
Wow.
Actually, it's sad, but it's funny.
Actually, I think I saw one of those, actually, where they're like beating someone with a stick. Like,
Yeah, it's crazy.
Man.
It's bad.
It's bad. Like all of my family members came to the family house, and like they're not able to go out now. They're all stuck in the same house. So like, yeah.
Yeah.
Anyway.
Oh, yeah. Let's do some easier stuff. Okay, yes, I wanted to say something about the exam. Yeah, we have not had a homework on this. And I have gone through most of what has been posted for homework 6. Do you guys feel comfortable enough to go through homework 6 again and just give a write-up? You see what
Yeah.
I'm
What do you mean?
like homework 6? Uh, I have covered most of that in the class, but can you guys in any way go through the steps, and like it is pretty much like going through my notes and filling up the homework sheet. But I think even that helps, I suppose, going through the instructions and going through the steps. Do you think you feel comfortable about doing that and just submitting a homework?
Yeah, sure.
So we're like filling in, you said we're like filling in blanks in homework 6 and then submitting that as homework?
Like homework 6, what I have prepared it as a homework, but I made it not due.
Right.
Like I think it is not due. So just make it due. But I've given you everything in the classroom. That was the point that
Okay.
let me not go through it. Let me not make it due because I'm going to be going through it in the class. But now make it due just so that you have a homework.
Okay.
Okay. So homework 6. Let us say Tuesday. April 7, Tuesday. And midterm 2. Is it possible to have an exam as we are doing now? Like, just make sure that your camera is focused on you. Let's say your hands and a sheet of paper, let's say, and we have an exam. Do you think that's possible? Or do you think?
Have the camera focused on us, our hands, and the sheet of paper?
Yeah, us means just the hands. I mean, I think I trust you guys. Just have the camera on. That's the only thing.
Okay.
Sure.
Okay. Like exactly like we have here. Then I have a proper assessment. That's all. That I can say that I had a proper assessment. And primarily, are you in touch with Harsha, Angela, any chance?
Not much. We just texted a couple of times about the virtual hours setup. He had some doubts about like how to set that up, things like that. But I think he's around, yeah.
So he's around, right? Yeah. Okay. So because yeah, I mean, I have to assess the students, so that's the point. So I think we will have an exam, but mostly I'll go over whatever we have done. I pretty much go through the class notes and homework problems. That's the main idea.
And so you'll give the paper in the beginning of the class, or you'll upload it the day before?
Let's say upload it 15 minutes before the class, and right after the class, you guys send it back to me. Right? Like it can be plus or minus a little bit here and there, but reasonable.
Okay.
Send it to you as in like cam scanner or something like that.
Yeah, there is a CAMS. Yeah, that's a good point. Are you aware of CAMScan? I think you will have to use that when you're submitting homework.
Yeah, yeah. That's
So
how that's what we've been doing for the quantum exam as well.
Yeah, so that is a CAMScan. Or use any software that's available. Send me a PDF file of your homework. Don't send me images or 10 images. That's not convenient. Just send me one PDF file, and CamScan does it. That's a suggestion, but I'm not trying to promote it. So use your favorite And I have used CamScan and I have been satisfied, but I rarely use it. Like once in 6 months or so I use it. It works out reasonable.
Yeah.
Again, class, whatever we went over in the class and the homework, that should be sufficient. It's just just for assessment. Don't stress out. Okay. 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 We want to do dynamics today, or let's call it relativistic dynamics, but we will start from whatever we did earlier. Let's call it dynamics because today we will introduce the idea of force.
You will send out a mail to the entire class saying that we have the exam. I don't have to inform Harsha. You'll send a mail, right? Just for that. He is in the loop.
Good point.
You can just send out a mail regarding all the logistics of the exam just so that he is also informed. That's all. If I say something and then I miss out some points, I don't want to be held responsible. So if you can just
No, you're not responsible at all. I mean, in
You
fact,
can't be responsible.
no, from a
I'm
friend
not responsible.
to friend
Yeah,
perspective.
I understand. Yeah,
I
you're
don't
not
want to lose it.
responsible at all. Even I'm not responsible to write to anyone about the exam. People are supposed to be there in the class, right? That's
Legally, yeah.
Yeah.
So, and that is what is making it complicated here. That like if he was there, then assessment would have been very easy. And like the last semester, I was lenient. After all this, I was thinking, okay, I don't want to. Like, he seems to be a very good student. I was very lenient. I ignored the whole thing, but I think this semester I'm not satisfied. So yeah, so I might not be lenient. That's fine. So that's why I'm doing all the logistics carefully, so that I'm not accountable to what, or I can be reasonable about it. I can give reasons. So because I think I can say it. I mean, I think midterm 1 was not. I didn't get midterm 1 on time from everyone of them, which and that is, and I don't get homeworks. So the course completely collapses if you don't have homework and midterms. Can be excused to a certain extent, but not completely. So yeah, so I think that's I shouldn't say more than you get the point. Yeah.
Right.
So yeah, so that's why we will have a midterm 2 for future one. That is just more for making it formal.
But do I tell him the exam is there?
How about this? This is recorded, right? Give him the link, right?
True, yeah.
Okay.
Right? This is recorded. Give him the link.
But they're in your web page, right?
Yes. Just ask him to, like, he's supposed to attend the classes at least that way, right? Including this conversation. I mean, Harsha is supposed to know. Like, I don't think I need to go and ask students to come and attend. I personally
Yeah,
don't
it's
think
not bad, but yeah.
Yeah, that's true. Yeah.
So, yeah, but yeah, hopefully things work out well. Yeah. Okay. Okay. So did I answer your question?
I guess, yeah.
Give him the link. Yeah, I think that's yeah.
Mr. Josh?
Yes, Justin.
The writing on the board is kind of blurry. Is there any way to like
Use the other board, I think, or I'll zoom it in. There are 2 boards that you see. I think one comes through my phone and one comes through one comes through my camera.
It's clearer now.
Now, is this zoomed in for you now?
It's better now, yeah.
But is it zoomed in?
It is not zoomed in, but it's.
Use the other window then.
Okay, how do I? It's set to switch to whichever one's speaking, and it stays on the one that's zoomed out.
Right click, use right click, and then choose pin. Pin the video.
Okay.
Right, that might do the job. Yeah.
Okay, yeah, it's there now.
Yeah. I have asked for why this happens is that my audio on my computer doesn't work and the camera is connected to the computer. So for the audio, I connect my phone.
Oh, okay.
But then the recording happens through the audio-based window.
Okay.
So it doesn't do a great job eventually. But I think I have asked for a Windows computer from the department just for this. I think I might get it today. Then I think this problem may not be there. So we might have one window and it might be there. Okay. So yeah, midterm 2, I didn't announce it here, right? So it is April 9th. And in virtual class, in Zoom class, however. Okay.
Yeah, before, sorry for disturbing. Just can you, the day before or just like 2 days ago, whatever topics you're intending to give a questions, can you give at least that idea? Because I kind of feel like it's dispersed here and there. I mean, I know that there's questions on relativity, but before that, we haven't done much after the elliptic.
Everything after midterm 1, right? And did we cover enough stuff? Yeah, what did we cover? I'll give you
just a list of topics. That's
basically I'll give you the homeworks that you have to go through. The homework usually topic dependent. Okay. Okay. Anything else you can think of? Yeah. Good. Okay. So we talked about 4 positions. X alpha, then we have we defined for velocity. That's derivative with respect to ds, proper distance if you want, or proper time, if we set up to a scale of c. And this comes out to be gamma times c, gamma times velocity. Then we define acceleration, alpha equals u alpha s times c. Oh yes, that's one thing I wanted to point out. There was a discussion about rest frame. That was a nice question that was raised last time by Justin, and we had a little bit of discussion there. And I think the point is that we're not talking about the rest frame. So there is a rest frame of the system itself, which is always at rest with respect to the person, correct? And there is another rest frame that you define, which is called the local rest frame. And by local rest frame, what you mean is that you stay in a frame in which the velocity is 0, not necessarily the acceleration. The rest frame of a person is in which you are at rest all the time. There is no acceleration in that frame. That is another rest frame in which the velocity at the instantaneous velocity is equal to 0, but not necessarily the acceleration. That's called a local rest frame. It means that you go to the frame in which the velocity is 0, not necessarily the acceleration. So that's the definition of instantaneous inertial frame. That's what it's called. LIF. Often they even use a short form for that. Instantaneous local inertial frame, you can call it. Okay? Okay. And we are talking about local inertia. All of the special relativity topics about
just when you started, I lost the internet. Can you slightly briefly?
Yeah. So the point is, I distinguish between two frames. One is a rest frame, in which v is equal to 0, acceleration is equal to 0, all the properties are 0. That means to say that at every instant you are at rest. So there cannot be any acceleration. But then there is another terminology or another concept called a local inertial frame or local rest frame. This means that you go to the frame at that instant, velocity is equal to 0. But A need not necessarily equal to 0. Okay, could be 0, but not necessarily. So you go to at that particular instant, what's your velocity? You set that to 0, but you could still be accelerated. Okay? This is also called local or instantaneous inertial frame. So it's called LIF. That should help with the discussion that we had last time.
So that idea is similar to, say I were to throw a ball in the air, and then when it gets to the peak of its flight, velocity is 0 relative to me, but in my Earth frame, there's still an acceleration on the ball.
Exactly. So then I think the discussion works, whatever we had last time. And where is it? Okay, so with that idea in mind, let's define our acceleration. Was defined as a velocity, rate of change of the full velocity, and we said that was equal to, it shows up as gamma times time derivative of this quantity, which is c times, here you can either get the velocity, which is gamma, plus velocity derivative. That was your acceleration, correct? And we showed that we got a more concrete expression for this, or more detailed expression, by using the value for this. This comes out to be v dotted with a over c squared times gamma cube. You can substitute that in. That gives you a proper expression for the acceleration. Most importantly, you have the length of this full vector. By length, I mean the magnitude of this full vector in the Lorentz sense. That came out to be the vector a squared times gamma 4, that's right. Or let me go first. So it is gamma raised to 4 What's beta dotted with A times gamma raised to 6. Okay. And immediately this has a clear feature that if A was perpendicular to acceleration, so if velocity was perpendicular to acceleration, that's what happens in circular motion, for example. This is circular motion. Or better, in a magnetic field, because we have to switch back to E and M very quickly. So think of a charge in a magnetic field, then that's equal to 0, and A alpha then is equal to square and gamma raised to 4. Even better, I can actually at this stage, I should say that this is the magnitude of the vector, but in the local inertial frame, gammas will be 1, and that's defined as the proper acceleration. Whatever is the length of this quantity is defined to be your proper acceleration. And to calculate that value, you go to that particular frame in which this has the simplest form, and it is clearly seen that if gamma was equal to 1, or when beta is equal to 0, this term always goes away. And in that particular frame, it will just be not square. And if I were to use that to represent the proper acceleration, then I have now. So you get the feature that magnitude of proper acceleration is given by square. Notice time dilates with a factor of gamma, but now acceleration dilates with a factor of gamma square, if you want. If you were going parallel directions, for example, linear motion, so this is linear motion, or when an electron moves, starts from rest in an electric field, then beta dot A is parallel to each other. So then we don't have to worry about the vectors. Then this becomes, oh, by the way, this is square. There's a tiny error here. This is not linear, this is square, right? So square there. So that's beta square A square in that case. There's already an A square. You can take that out. And together, this leads to the fact that this is gamma 6, factor of 6 comes up. And that leads to gamma 2. So the acceleration transforms very differently from time and length, especially when it is perpendicular or parallel. They have a different factors of gamma that dilates or contracts it. It's a matter of I think if you think of this as the acceleration, then with respect to the rest frame, that is getting contracted by a factor of 2. Right. Okay, so that's acceleration, but now and this is what we were doing last time. And now let's introduce what is force. Any questions at this stage? Okay. So now we want to define what is force. And let's so let's equal to F alpha will be complete. There are two ways we can define it, either dp alpha over ds, right? That's your purpose, and a factor of c, or we can also say this is simply mass times, like remember p alpha is u alpha, mass times u alpha. That's also mass times acceleration times alpha. So that will be your Newton's law, generalization of the Newton's law. But this is now 4 force, and that's your 4 acceleration. Where is your actual force that we are familiar with setting? So let's look at it more closely. So F alpha is nothing but c times dt over ds, and d by dt. That's a chain rule here. And momentum was, remember, energy over the 0th component was energy over c, and the space components were just p itself. But this is not your Newtonian momentum. This is mv times gamma. Recall, p is m mass times velocity times that is a factor of gamma there. Your Newtonian momentum is simply mass times velocity, so there is no factor of gamma. So that's your force or 4 force, but let's use the factor of gamma to expand this out. So there's this gamma because c times dt over ds is gamma, and and we have 1 over c times I'm missing anything? No, right? Yeah, so this is dE by dt, and this is dP by dt. And this would be your old force, right? Rate of change of momentum with respect to time. That's your old Newtonian force. But remember that this P has an added feature in there. So there is a feature of gamma in that. Up to that, if not for that, this is exactly Newtonian force. Or you can say that whenever it hits your velocity, that's mass times acceleration. That's your Newtonian force, and that there is an added feature to that. Okay. Any questions here?
Yeah, one question. The last equation that you wrote up on the board there, so the dP dt that's in that, is the gamma still in there, or is in that?
That's gamma is still in there. So let me clarify that. So that is gamma times 1 over c dE by dt. Right, and this is a mass times acceleration times gamma. Like when I can hit the velocity, or I can hit the gamma, right? Plus mass times velocity times d by dt. That's your Newtonian force. That's the Newtonian force. If I were to call this F, that's the Newtonian force. So this is an additional feature that comes only in relativity, right? A velocity dependent quantity, and the rate at which gamma is changing, that also contributes to a force, right? That's very much like the acceleration. In acceleration also we had a similar quantity here. So that's exactly the same term. So multiplied by mass m. And there. Okay, clear? Okay, so let's do, so most of the equations are changing, correct? Like your Newton's law is no more pretty much the same as our Newtonian physics, but there is one equation that remains exactly the same, at least in the form that we will see, and that is that let's calculate f alpha times u alpha. So let's recall u alpha is minus gamma c times gamma times velocity. If it was u covariant vector, then it is plus gamma c times gamma v. So if I were to do a covariant version of that, so then it is minus of that. So let's calculate f alpha times u alpha. And what will that be equal to, by the way? Of course, I have to multiply these things, but in general, what is that equal to? From what we did last class? Right, this is, remember, mass times acceleration times u of alpha. What is that equal to? Any? Try to recall from, like we had argued that one can see it right away here. Let's see, u alpha, or you remember this? How much was it?
Minus c square.
That's minus c squared, right? If I take a derivative of this, I get acceleration times u alpha, like 4 acceleration times u alpha. On the right hand side, this doesn't change, so that's 0. Right? 4 acceleration and 4 velocity are perpendicular to each other in the Lorentz sense, right? Not in the spatial sense. So that's equal to 0, which allows us to infer something. So that means force times the 4 force times the 4 velocity is also perpendicular to each other. Then what can we learn? You can multiply these two quantities. So let's do this. So it is minus gamma square times dE by dt. What is rate of change of energy with time? In the Newtonian picture, there's a
Power,
right? Change in energy with time. So that's power showing up. And this one, let me define this to be the force, right? So this can be the force F, right? With the understanding that this force has both velocity and acceleration term in it, then we can write this to be plus gamma square. It's still in the window, yeah. So gamma square times F dotted with V is equal to 0. And gamma square cancels out. And probably I'm out of the rate of change of energy with time, which is of power, is equal to F dotted with V. And that equation is the same in Newton's law, Newtonian physics also, remember. Work done is force dotted with displacement divided by time. So you get displacement by time. So that's force times velocity. So this equation is true both in relativity and non-relativistic physics. So that's one relation. And once we have this, we go back and substitute dE by dt in here. And that's what we have our Newton's. And we will do some specific example. So the 4 force is equal to gamma Yeah, I think the best way to write this is, since I've covered everything, we will define the spatial part of force as ma times gamma plus mv times gamma over dt, and force dotted with velocity is equal to dE by dt. These are the two equations you need whenever you're working with relativistic physics. F is first, and that F dotted with V is dE by dt. And let's see. Let's do an example, right? The first example you do in Newtonian physics is when something is going with uniform acceleration, right? That's the first non-trivial example. You see something going with uniform velocity is too straightforward. There is nothing interesting going on. But the first interesting piece is when something is going with uniform acceleration. So let's see what what is the physics associated with that. So let's go back and look at the equation that was involved with uniform acceleration. Right? So uniform. You don't have to say uniform proper acceleration, I suppose. So proper acceleration. So now we are talking about a particle that's moving with proper acceleration all throughout. So we are telling that what is an equation, or what is the orbit, if you want to say, but this is all going in one line. What is the equation, or what is the curve that represents the path of a particle that that is uniformly accelerating with proper acceleration a naught. So and remember, so we are talking about velocity is parallel to acceleration. So velocity parallel to acceleration, if you go a few statements before, we have the situation that proper acceleration a naught times gamma cube is equal to a naught. If velocity is parallel to acceleration, everything is happening along the same line. We don't have to worry about the vector signs. So we can say this is d v by dt times gamma cube is equal to a naught. Again, this is the acceleration in an arbitrary frame, and this is the acceleration in the local inertial frame, right? When you can choose velocity to be 0 at that instant, then acceleration comes out to be a unique number. Let's since gamma is given in terms of beta, so let's write the equation for beta. We can divide it by c, so I can replace velocity here with beta, and this becomes a naught over c. Right? That's the equation that governs a particle that's moving with uniform proper acceleration. To see this slightly better, let us do the following. Let's have an identity. So let's try to see what happens with d by dt of beta times gamma. you'll make an observation that actually this will be the left-hand side out here. So that's going to be an identity. But just let's take this derivative. So this is d beta by dt times gamma. Right? I can either hit beta or gamma. And this is plus beta times gamma. But remember, an identity we wrote down right in the first part of the first board. Let me rewrite that here. Gamma by dt is equal to velocity dotted with a, but since it's all in the same direction, I can just say this is v times a by c squared. So if I were to use that piece in here, so this is d beta by dt times gamma plus beta, and d gamma by dt, this is the same as beta times d beta by dt, right? So this is d beta by dt. That's beta squared times d beta by dt. What's wrong here? Something is wrong. Oh, something went wrong here. Oh yeah, I did not copy the correct equation, right? So notice one. So in the first board, the derivative of gamma with respect to time is velocity times acceleration with a gamma cube in there. Right. So I have to be careful. So let me rewrite that. So writing that again. So gamma by dt is v times a over c squared times gamma cube. So that makes it, so that's the same as beta times d beta by dt times gamma cube. So there is a gamma cube in there. So what is that equal to? I think you guys have still, the board is still there. Okay, now. So that gives you beta by dt times gamma and 1 plus beta squared over 1 minus beta squared. Gamma squared is 1 minus beta squared. So that's 1 over 1 minus beta squared, and there is a so that's 1 over, so that's gamma squared. So that makes it beta by dt times gamma cube. Okay. So this was the equation that governs your proper acceleration, which is the same as saying that we have gamma cube times d beta by dt is equal to a naught over c, but that's also equal to time derivative of this. So that makes the differential equation very easy, and in fact we can solve this. So when something is going with constant acceleration, this is also called Rendler acceleration. And that connects with the book that I suggested. That that's the same Rendler, right? He wrote the book also. So what we have is the equation for proper acceleration is d by dt times beta times gamma is equal to a naught over c. That's the equation we want to solve. Remember, this is a constant. We're keeping this to be a constant. That's a proper acceleration. And this is velocity. Remember, beta is velocity, gamma is 1 over 1 minus beta square root of that. So this whole time derivative of this has to be constant. That's a straightforward linear differential equation. So we can immediately say that beta times gamma, the product of that is equal to a naught over c times t plus a constant. Okay. Whenever we talk about a particle going with uniform velocity, we can also ask what is its velocity at time t equal to 0. Right? So let velocity means beta, right? Beta at time t equal to 0 be equal to 0. That means this starts from rest, right? It is starting from rest. And if that is the case, this is equal to 0 at time t equal to 0. That means constant is equal to 0. This implies that constant is equal to 0. So that's a very special initial conditions we have chosen. Otherwise, things only move around a little. So that's done. So, and then we have beta times gamma is equal to a naught over c times t. We are interested in the position, right? If it was going with Newtonian uniform acceleration, we would say it's a parabolic curve. We would like to see what is the curve in this scenario. So let's square this quantity so that there's a square root inside this gamma that can come out. So this is beta squared over 1 minus beta squared is equal to a naught squared over c squared and times t squared. It's still dimensionless because acceleration over speed is 1 over time, and that is a time square. Let's solve this for beta because we can get beta on one side, right? Currently, time is on one side. So this is the same as, it's still, yeah, I can write one more line, I guess. So it's beta squared is equal to a naught squared get this onto the left, and we learn that, let me change. So that's beta squared correct. Again, we are looking for position, which is velocity's derivative of position with time. So this will be, so beta, which is 1 over c times dx by dt. Correct. That's your beta. I take the square root on the right hand side. So that's a naught over c times t divided by square root of 1 plus And presumably that equation is easy to solve. Okay. So if you want to solve for position, we have to integrate this with time. So let's any questions until here? So again, let me rewrite this. So this is 1 over c. So this is dx over c. That's equal to a naught over c times t divided by 1 plus square and dt. I could integrate this on both sides. Let's say we are integrating from plus a constant. Plus a constant. When we integrate, we get a constant. It has to be written after we do that. So that's x as a function of time over c. That's equal to, what is that integral equal to? Let's substitute 1 plus a square over c square times t square as u, let us say. So that is everything inside this square root can be defined as u. Then we have a naught over c times a naught over c times t, and q is equal to times dt is equal to du. That's already there in the denominator, sorry, numerator. So that's du times c over 2 a naught. This is integral of du times, I have to invert that, so it's c over 2 times a naught. And in the denominator, you simply have square root of u. That's what this plus a constant. We haven't done the integral yet, so no. Integral of u is u raised to minus half plus 1 du. So this will be u raised to half and 2 times that, right? The factor of 2 goes away. So this is equal to c over a naught times u, but u was square root of 1 plus a naught square over c square times t square. That's your x of t over c. So I multiplied by a c square there plus a constant. That's your c square, c over acceleration. There is a time in the numerator, and then there is a remaining c, so that comes out to be actually x. So that's your curve representing this motion. But let's try to make this a little better. So let's say, let's fix the constant also. So remember, we already set at t equal to 0, we had the velocity to be 0. But now let's ask, what is the position of the particle at t equal to 0? So let.
Mr. Josh, can I ask you a quick question?
Yes.
I don't know if it makes a difference, but when you found the 2 times u to the 1/2, should that have been negative 2? Because it was u to the minus 1/2 that you took the.
Because this is 1 over square root of u, right?
Right.
U raised to minus half.
Oh, sorry, I'm going the wrong way. Yeah, you're right.
So I think you do minus half plus 1 divided by same quantity, right? So,
Right.
I think that's okay.
Right. You're right.
Yeah, yeah. Yeah, but good. Good observations, yeah. So let at t equal to 0, so let's say x of 0. It is always possible to choose that to be 0, but this time let us try to be a little clever about this. So let's say that it is not at 0, instead it is having this particular position, and that is just so that there is this cancellation of the constant that comes in. So let's see what this is at t equal to 0. At t equal to 0, right? Or x of 0 is. So what does that mean? So x of 0 is equal to c square over a naught. At t equal to 0 from the right hand side, that's again c square over a naught plus the constant. That allows you to set the constant to be 0. So that implies that the constant is equal to 0. Well, that's just a very special choice so that you get a simple relation. So our equation is, we should go down. So our equation is x squared. Let me, so that's equal to, so it's c squared over a naught, the whole square, plus c squared over a naught times t squared. Am I correct?
You're just squaring that expression, x of t equals to.
Yeah. That's all I'm doing. Did I write it correctly?
There will be more terms, right? With some square root involved as well.
Oh, did you say that? Okay, let me do this. So let's. So if I square the, can you guys see? Yeah, you guys can see both, right? So if I square it, so this is x squared is equal to c raised to 4 times a naught times 1 plus a naught squared over c squared t squared, right? That's pretty good.
It's
Not be squared.
I squared this equation.
but you have a constant as constant is 0. All right, cool.
The constant I found to be 0, correct? So that's gone.
Yeah, then it's just that. Yeah.
Right.
But why?
So-
Why?
Yes.
Like a naught that's under c to the 4, the a naught should not be squared.
Yeah.
Yes. A naught should also be squared.
So was the x naught equal to c squared by a naught your choice, like
That's
for
a very
convenience?
special choice. That's a very special choice. I was. That's kind of a. So that constant is 0.
Yeah, it's for our convenience, right?
That's
how-
only for our convenience, and we will see once I get the solution. In the solution, we will see where that point is. So when you choose it to be 0, it's not really convenient. It strips the whole thing.
Okay.
We will plot this and we will see a nice feature. So that's the same as e raised to 4 over a naught squared plus c square over, oh, that's the acceleration has to cancel. That's what earlier it was not happening. Not getting c square, nice. Correct? So our equation is x squared minus t squared is equal to e raised to square over a naught square. If this was a plus sign, that's the equation of a circle. If it's a minus sign, that's the equation of a hyperbola. Okay. So what's that represent? So let me. Okay, so our equation is x squared minus c squared, t squared is equal to c squared over a naught. There is only one parameter in this problem, and that's c squared over a naught. Right. So c squared over a naught is also our x of 0, right? That's x of 0. At t equal to 0, that's where that particle is. If you were to plot this, this is our x, and that's our ct. At t equal to 0, it is a c square over a naught, which is dependent on your proper acceleration. That's somewhere here. That's your c square over a naught. And then it behaves like a parabola or a hyperbola, and that's your. So that's the hyperbola that you have. But we also know, so that's your curve that represents a particle moving with constant proper acceleration, not a what is the most analogous quantity to a uniformly accelerated particle relativity. That's something going with constant proper acceleration, and that's the curve for that. Any questions at this stage? I'll do a little more at this point. I will, at some limit, when things are going slow, this should lead to a parabola, right? In some limit, this equation should lead to your half gt squared, correct? So let's see how that comes about. So let us so let me write the equation.
What do we mean when we say t is small? I can understand small.
What I mean is when things go smaller than speed of light. So let us ask, what does that condition mean to begin with? Okay. So something velocity should be small, right? So when we are starting from rest and picks up speed, correct? That is what is happening at this point. At least our problem, this equation represents a particle that starts from rest at x of 0 equal to some constant, and then it starts accelerating, so its velocity will start picking up. Right? So in the early stages, when time is really small, we expect its velocity to be very small. Right? That is when it is non-relativistic, if you want. Does that make sense? To save for small time. So that is what I'm going to do. So let me write x here to be equal to c squared over a naught squared plus c squared. Oh, sorry, this was x squared, so I have to take the square root of it, right? So let's bring this out. Square over a naught and square root of 1 plus. This whole thing goes in the denominator, so that is a c raised to 4. So let me, how do you say this? So c squared, t squared, c raised to 4 times a naught squared. Reasonable? And so now let's ask what is small. So you ask the question, what exactly is the small parameter here? So we are saying that this t squared a naught square over c square. That's that quantity here, c square cancels out. This has to be small. Or it is equivalent to saying t has to be very much small compared to c over a naught. Okay, so that means only in the initial stages, not when it has picked up sufficient speed that it is going very fast. When it is going really slow, it is pretty much non-relativistic. Like Newtonian physics works when things are going slow. Correct? So in that case, this whole square root can be expanded. C squared over a naught. And this is 1 plus. Remember the binomial expansion. This is half. Like square root of 1 plus x. The square root of 1 plus x is equal to 1 plus half of x, right? Approximately the leading order. That's half of t squared a naught squared over c squared of higher orders. This is your x of 0. That's x of 0 plus c square cancels out. Notice c square cancels out. One of the a's cancels out. So indeed, this is your half at squared, correct? That's your Newtonian parabolic motion sitting in there exactly, and our proper acceleration sits in there properly in the very right place. And indeed, that's what one would expect. So everything fits in very well. But the moment it starts going a little faster, then that approximation is no more correct. Then it indeed goes as a hyperbolic motion. And this whole problem is called the Rindler motion of the particle. This is flat. It's all flat. There is no curvature involved. Because general relativity, whenever you think of acceleration, you think that there is a curvature involved. There is no curvature here. This is all flat space. Everything simple, special relativistic. So that's all we will work on here as far as relativity construction goes. Next time we will come back and write electrodynamics in this language. Now that we have built this language, we will write electrodynamics, our Maxwell's equation, using these properties, and then talk about how things look like when something is moving, how electric field changes. Like in relativity, everything is about how different observers see different things. Velocity, how does it look like to a different observer? Acceleration, how does it look like to a different observer? Force, how does it look like? And now we have more features like electric field and magnetic field. And the observation will be that electric field and magnetic field are not vectors. They are actually components of a tensor. So that will be the observation we'll make. And from that point on, we'll see how it transforms. Okay. So let's stop here. And we'll go from there. Okay. Any questions?
No.
Okay. Yep.
See you next time.
Okay.
Bye.
See you. Bye.
Okay.